We're going to look at 3 problems, and in these 3 problems we can see the relationship between the idea of slope, the idea of average rate of change of a function f, and then the generalization, the difference quotient of function f. Let's remind ourselves of the formula for slope of a line. Okay, there's 2 ways we could write down that formula, at least 2 ways. 1, the slope m of a line that contains the points x1, y1 and the point x2, y2 can be written down as the ratio change in y over change in x, where we take y2 minus y1 in the numerator and x2 minus x1 in the denominator. Order matters in how we write down a difference, but if we choose to put the difference y1 minus y2 in the numerator, we can record the difference x1 minus x2 in the denominator. Okay. So to practice using the formula for slope, let's look at this problem. Let's find the slope of line PQ if point P is 1, 4 and the point or the ordered pair Q is 2, 1. Okay. So the slope of this line, and we might want to put a subscript PQ just to, this would be the segment PQ. It's going to be a ratio. Change in y values over change in x values. Well, if we choose to write down y value 1 minus y value 4, 1 minus 4, then we need to write down the difference 2 minus 1 in that order. We see that the numerator would be -3, the denominator would be +1, and that ratio would reduce to the integer -3. So PQ would be a line that descends from left to right with a slope -3. Okay. Now the average rate of change of a function is also a ratio. Let me slide this paper in here. Let me remind you of the formula for average rate of change. So if we're considering a function, let's say f, on an interval from, let's say, a to b, then the average rate of change of that function is the ratio f of b minus f of a over the difference b minus a. It's similar to slope. Do you see it? We have the difference in the outputs over the difference in the inputs for function f. Change in output over change in input. Okay, I've chosen a function, kind of simple function. We'll look at this parabola. Let's say that f of x is 5 minus x squared. And let's calculate the average rate of change of this function f from x equals 1 to x equals 2. Okay. So f is the parabola, and the interval we're considering is the interval 1 to 2. Okay. Okay, let me slide this up here again. Let's do our calculations. Average rate of change is a ratio. We're going to write down f of 2 minus f of 1, and we'll divide that by the difference 2 minus 1. Well, our function is this parabola, this quadratic function, 5 minus x squared. So we're going to need to calculate 5 minus 2 squared, and then take away 5 minus 1 squared in the numerator. Everywhere there was an x in this function, we replaced it with the input, first 2, then 1. So 5 minus x squared became 5 minus 2 squared, and then we took away 5 minus 1 squared. Now we need to simplify according to order of operations. So we'll do everything inside this set of grouping symbols. We'll calculate this set of grouping symbols, and the last thing we'll do is divide by 2 minus 1, which simplifies to 1. Well, 5 minus 2 squared is 5 minus 4, or 1. And 5 minus 1 squared is 5 minus 1, or 4. So our average rate of change is -3 over 1, or the integer -3. Okay. I'm hoping that you see some similarities with the calculation of slope from before, and if you need to pause and look back, you might see that we end up with the same ratio eventually. Okay, let's move on. The generalization of average rate of change is called the difference quotient of a function f. Okay. We still have a ratio or a quotient. We have a difference over, it ends up being a simplified difference. If you let me do some scratch work over here, if I take the input x plus h and I subtract an input, let's call it x, then we can combine like terms. X take away x is 0, and we're left with h. So the difference quotient I have here in black could be expanded. You don't have to memorize it this way. But we have the difference in these outputs, and then we'd have the difference of the corresponding inputs. And again, in green down here in the denominator, x take away x is 0, leaving you with h. So this indeed is the generalization of average rate of change. Change in output over change in input. Okay. I'm going to use that black formula for this last example, and then we'll look at a picture that might bring some of this together for you. Let's again consider the function 5 minus x squared. And now let's calculate the difference quotient for function f. Okay. So we need f evaluated at the sum x plus h. So that would be 5 minus the sum squared. And I might put grouping symbols around that. We need to take away f of x, which is just the function 5 minus x squared. And we place that all over h and hopefully simplify. Okay. So I have the function evaluated at the sum minus the function just evaluated at x all over h. The first set of grouping symbols, I need to square the binomial. If you do some FOIL off on some scratch work, you'll find that you get x squared plus twice xh plus h squared when you take x plus h times itself. Okay, I'm going to write down the remaining terms, and then we'll simplify again. In the first set of square brackets, I need to distribute the subtraction. I'm subtracting x squared, but I'm also subtracting the cross terms 2xh. I'm also subtracting h squared. A person might think about an understood -1 being the coefficient in front of those set of parentheses, and a person might think about distributing the -1 to those last three terms. Okay. Now we can go ahead and distribute this subtraction. We can subtract 5 and subtract -x squared. So in green I would record minus 5 plus x squared. But if you need to pause and think about it, in front of that first set of square brackets, you can also think of that as an understood coefficient of -1, and we would distribute that coefficient using the distributive property. Okay. And now to simplify even further. And I see a mistake that you all may have caught. I need to cross that out. There's no h squared on the bottom. Nothing magic should happen. Okay. Well, in the numerator we have 5 minus x squared minus 2xh minus h squared minus 5 plus x squared all over h. We really don't need that first set of brackets. The associative property says we can take them away. And we see that the constants 5 and -5 cancel because they add up to 0. And we have these terms opposite x squared and x squared, a negative term and a positive term that also add up to 0. So we've simplified the numerator to two terms. I'm going to go off to the side here. In the numerator there's a common factor of h. And because h cannot be 0 from the definition, we can cancel these h's. H divided by h is 1. So that leaves us with the difference quotient, negative 2x minus h, where x does not equal 0. Okay, thank you for your attention, and do feel free to rewind and look at these calculations more slowly, or think about how you can simplify this quotient in your own way, but arrive at an equivalent answer. Okay. Good luck.